Should have finished the chapter 19 homework, which I will check during the break. Okay? And if you have finished it and it's correct, then I will reward you with a unicorn stamp. Meanwhile, this week we will cover chapter 20 on nuclear chemistry. This is the last chapter from the textbook. But just as a reminder, okay, next week, next Monday, is your lab exam. Then the 4th of December, we will be doing a review. Okay? Next week, we will be doing a review. I will have a study guide prepared to kind of review some of the stuff that I think is important, to review the multiple choice questions. Okay? I really would not skip next week just because it is a review. As you guys all know, the review really is your chance to ask questions and work through some things that maybe aren't clear. Okay? The exam will be split up into 3 parts. Part 1 is the multiple choice worth 100 points. Part 2 is also 100 points, and it will be the material from old exams. So exams 1, 2, 3, and the midterm. And of course, the last part worth 100 points is going to focus on the new material, which is chapter 19 and 20, which will be on electrochemistry and nuclear chemistry. Okay? I have posted quizzes for the last 2 new chapters, chapter 19 on electrochemistry and chapter 20 on nuclear chemistry on Canvas. Highly recommend that you guys all do the quizzes. Okay? Don't forget, top 5 scores on the online quizzes do count towards your final grade. So if you don't do any of the quizzes, you automatically will receive a 0 out of 100 when I calculate your final grade, and your grade will drop by about 5%. Okay? It's just the way the point system works. Okay? How many times can you take the quizzes? Unlimited number of times. So everyone should get a 20 out of 20 on at least 5 quizzes. Listen, the quizzes are open up until the day of the final exam. They close the day of the final exam. Okay? So it is a good way to review for the final exam, right? Do every single, because there's a quiz on every single chapter. Just do the quiz on every single chapter. Make sure you get good points. I would redo the exams again. Okay? Part 2, I'm just going to pull questions straight from the old exam, change some elements, change some numbers, but pretty much straight from the old exams. Okay? And part 3, of course, again, from the homework and from the Canvas quizzes. Okay? Any questions? There is a very important thing to note, though. Okay? Now, the class normally starts at 9:30, right? Okay, lecture. But because it's a final exam schedule, the exam is not at 9:30. So I want you to all take out your planner. Okay? And on December 11th, okay, the final exam starts at 10 a.m., not 9:30, 10 a.m. in this room. 10 a.m. in this room. Okay? Again, not at 9:30, 10 a.m. Okay? And it goes until noon. Okay? Please, December 11th, please make sure you write that down or note that down in your planner or your electronic device, whatever is your notation of choice. Okay? Any questions? And we know where when and where the lab final is? Next Monday at 9:30. So remember, the lab final is at 9:30 on Monday. The lecture final starts at 10. Is that clear? Super clear? Okay. Yes?
So the in-class quizzes are also the top 5?
Yes, the in-class quizzes are also the top 5. Today is your second to last opportunity, and then next week will be your last opportunity. Okay? Next week's quiz will be on nuclear chemistry, and that will be your last opportunity. Okay, I've given, I believe, 7 or 8 quizzes at this point, right? Okay? So you should have collected plenty of good scores. Okay? Yes, they're 10 points each, the top 5, right? Goes towards your final grade. Any other questions?
On December 9th,
Usually your grade will go up a little bit when I do that because some of the lower quiz scores will be dropped. Unless, of course, you didn't take any of the quizzes, in which case your grade will probably not change or maybe get lower. Okay? Yes, Mercedes.
on December 9th, we don't meet, we'll be done with block time, so we won't meet Monday, December 9th?
Right. December 9th, there will be no class in terms of the lab. I won't be there. Mercedes won't be there. Shabana probably won't be there. Uriel, will you be there?
Yeah.
Unless you want me to hold the class and then we can review in terms of any last minute questions for the lecture. Would you want to do that? Okay, so let's do that. December 9th, okay, at 9:30 to noon, okay? It'll be in the lab room though, not here, because there'll be a class in here. So it'll be up in the lab room where we normally have lab. And I won't have any new lecture or new material. The plan is just going to be, you can ask questions, I will entertain questions, and you can come and go as you wish, okay? It's like extra office hours, okay? Anything else? Any other questions? It's a good question, Mercedes. Okay. All right. Okay. All right. Nuclear chemistry. Don't worry, the quiz will come later. We're going to change things up just a little bit. We're going to do the nuclear chemistry first, finish this chapter, and then take the quiz. Okay. Lexi's like, no, I need to take it down. It's fine. You'll be fine. You guys will be fine. All right. So, since the beginning in 130 or 151, whenever you joined our class, okay, we talked about chemical reactions. We said double displacement reactions. Last chapter, we talked about redox reactions, which is the transfer of electrons. Okay? All of these chemical reactions, the element numbers never change, right? If you started off with 3 carbons, you should end up with 3 carbons. If you start off with 20 hydrogens, you should end up with 20 hydrogens. Okay? The only thing that really changes is the electrons and how they're bonded together. That is really the only change. Okay? These are called chemical reactions. It involves electrons only. And electrons, remember, are often chemical bonds. Right? A single bond is 2 electrons. A double bond is 4 electrons. Triple bond is 6 electrons. Good. So really, when we're doing a chemical reaction, we're talking about bonds being broken. And then, as a result, new bonds are formed. Okay? And as a reminder, chemical bonds are electrons. So if you have a redox reaction, there's a loss or a gain of electrons. Okay? So remember, with chemical equations, we're talking only about electrons. Okay? But now we're going to switch gears a little bit, and we're going to look at nuclear chemistry. And this involves changing the composition of the nucleus. I.e., what is in the nucleus are protons and neutrons. Okay? Let's just take a moment. If I change the number of protons, okay, is everything going to be the same in terms of the element identity? No. If I say carbon from the periodic table has 6 protons, right? If I did a nuclear reaction and lost a proton, am I still carbon?
No.
What would I be? If I lost,
Boron.
I would be what?
Boron.
Boron. If I lost 1 proton, I would be boron plus 1 hydrogen. Right? You agree? 1 proton is lost. That proton is the hydrogen. The leftover is your 5, which would be your boron. Right? Do we agree? Okay. So when it comes to nuclear chemistry, the element number is not conserved because element identities are changing. Does that make sense? Okay? And just as a quick review, remember electrons are on the outside, protons and neutrons are on the inside. Okay? We talked about protons and neutrons in particular when we talked about isotopes and isotope symbols. So this should be a review from back in the day when we first did chemistry. Okay? I remember 1:30 I would talk about this like the first week of class. Okay? Isotopes are atoms that had a higher or lower neutron count, and thus affects the atom's mass or the atomic mass, right? In fact, in lab, we talked about isotopes. Let's review. Ready for the lab final on next Monday, right? Okay. For NMR, who remembers what solvent we use? CdCl3. What is the CD? What is the D? Deuterium. And for those of you who are paying attention, okay, what is deuterium? Let's look. Okay, regular proton is hydrogen. Okay, and it is one proton and one electron. Okay, does it have a neutron? No. That's why the mass is 1 on your periodic table, right? And I would say that most hydrogens are this isotope form. So you have 99.985% abundance. So 99.98% of the hydrogens you naturally look at is this kind of hydrogen. Okay? Deuterium, CdCl3, that's the D, right? What is the difference? It has a neutron. This yellow ball is the neutron. There's an extra neutron. So if you're looking at it, what is its mass? Andrew? 2, right? Because the electrons don't weigh are negligible, right? So in terms of mass, electrons are negligible. So you've got 1 AMU, or 2. Okay? There is something called tritium, okay? And it is still 1 proton, but it now has two neutrons. Okay? Okay? Oftentimes, I don't know if you've heard, like in television shows, they'll be like, you want to make a bomb or something? What do? You get some heavy water, right? What is heavy water? Heavy water is just, instead of H2O, it's D2O. So you have deuterium instead of hydrogen. So D2Os. And why do they call it heavy water? Is it heavier? Yeah. It is. 1 neutron heavier, every single hydrogen, right? Make sense? Okay. So when we have CdCl3 in lab, what was the point of using it? Why didn't I just use CHCl3? CHCl3 is cheaper. CdCl3 is super expensive. Why would I waste my money to buy you CdCl3? Who remembers? No? Right, so we're looking at, in NMR, we're looking at how many hydrogens and what kinds of hydrogens, right? If we have a bucket full of CHCl3 as our solvent, that peak will be super, super tall, and then you won't see any of the peaks that you're interested in, right? The CdCl3, that peak is shifted way out of our window, and so we can see just the hydrogens that we're interested in, because the CdCl3 has an extra neutron, so it's outside the window, and we're looking at hydrogen, right? That was the whole point, right? Make sense? All right. Now, in terms of keeping track of how many protons and how many neutrons, oftentimes we would like to use the isotope symbol. Some books call it the nuclide symbol, so it's either the nuclide symbol or the isotope symbol. They mean the same thing, okay? And really you have the element symbol here, or the atomic symbol. So for carbon, it would be just C, right? For hydrogen, it would just be H, capital letter, okay? Now the mass number needs to be up high in the left-hand corner. Mass number is just the total mass. And the atomic number would be the number of protons. Okay? So obviously, if you subtract the mass number and the atomic number, you will get the number of neutrons. Very good, Andrew. Neutrons. All right. So let's see how we would represent a nuclear equation. Okay? So in this chapter, we're going to learn how to write nuclear equations. And that nuclear equation should represent the charge inside an atom's nucleus. Okay? It's almost like we're just looking at the nucleus and we almost don't care about the outside electrons. Okay? So we're looking at uranium-238. What does the uranium-238 mean? What does the dash mean? That's the mass, right? The 238 is the total mass. Okay? It decays and loses an alpha particle to become thorium-234. Okay? So what is an alpha particle? Okay, it's a helium nucleus. In fact, an alpha particle is really just 2 protons and 2 neutrons. If it has 2 protons, let's look on our periodic table. If it has 2 neutrons, it has to be what? Sorry, 2 protons. If it has 2 protons, it has to be what? Helium. So we write He. Okay. 2 because there's 2 protons, right? How many neutrons? There's also 2. So add that together, you get 4 as the mass. Right? So this is an alpha particle. Okay? So I'm going to keep a running tab here because there's going to be lots of different particles that we're going to encounter today. And just as a quick reminder, sometimes in this chapter, for some reason, you guys forget the basics. Please don't forget the basics. When you pull an element symbol or an atomic symbol off the periodic table, the first letter is capitalized. The second letter must be lowercase. If you don't lowercase that second letter on an exam, I will mark it wrong. Okay? First letter is capitalized. The second letter must be lowercase. Okay? So, if we're looking at it, we're saying uranium decays and forms thorium and helium, or the alpha particle. Okay? Now, on the homework, oftentimes I won't tell you what it decays. I will just tell you that uranium decays and loses an alpha particle. Okay? So you've got your 238, you've got your uranium, and you've got your 92. Okay? It decays and forms something. I'm going to draw boxes just for now to help you guide you. Okay? Plus your alpha particle. Can you figure out what this was if I didn't tell you? How would I figure it out? It just seems like a lot of empty boxes, right? How would I figure out what is the element symbol? What is the mass? And what is the atomic charge or atomic number here? Okay, so 92. I've lost 2, right? So really this must be 90. Okay, kindergartners can do this, right? Okay. The total mass was 38. I've lost a total of 4. So this mass must be 234. Probably should have drawn the box a little bigger. Okay? So how do I know what's this box here? I look at the 90 and look at my periodic table. Box number 90 is what? Oh. I remember, H must be lowercase. Okay? To me, this is just like a game. It really is. It's just a game, right? Okay? If you can subtract and add, you can do this. Okay, now, let's read the box together. It is often not necessary to indicate the chemical compound or electron charges for any ions involved. Okay? Sometimes these things have charge. We don't need to indicate it. Okay? Normally in an isotope symbol, sometimes you put a little 2+ or a 3+. For this chapter, you are free. Okay? Don't worry about that. We're worrying about the mass and the number of protons. All right. So, there are lots of different kinds of subatomic particles other than the alpha particle. Okay? Now, other than the nuclide or isotope symbol, some important symbols are these subatomic particles. Okay? For a proton, and I would, right now, take some notes and write it down. A proton we're going to represent as 1H like this. Okay? Why 1 here? Because that's this number from the box on your periodic table. Why is this a 1? Because there are no neutrons. Okay? Another way to represent it, and the book will represent it this way sometimes, is 1, 1 and P. Okay? A neutron, okay, is 1, 0, and N. Okay? 0 because it is not a proton. It does not have an atomic symbol. Okay? But 1 because its mass is equal to a proton, which is 1. Everyone with me? Okay? Electron is 0 minus 1 E. Okay? This will help us to keep charge of certain things. We have the minus here. And again, its mass is 0. Electron's mass is negligible. So if you lose an electron, the mass shouldn't change. Okay? Now this is something very special that we have never encountered before. Okay? What is a positron? A positron. It is a positive electron. That is correct. Okay? Just like a normal electron, it has no mass. Or not no mass, I should be very careful. It has negligible mass compared to a proton or neutron, right? So that's why this is 0. But its charge is actually plus, not minus. Okay? So you can lose just plus charge and no mass. I repeat again. You can lose a plus charge and no mass. Okay? Just losing charge. Okay? And of course, these two have corresponding symbols. Sometimes they'll write it like this. Okay? And last but not least, you have a gamma photon. These are usually found in space, right, and not on Earth, unless you're doing a nuclear reaction. Okay? And it is 0, 0. It is like basically losing pure energy. You're not losing charge. You're not gaining charge. You're not losing mass. You're not gaining mass. It's just pure energy. Okay? This I would keep handy while you're doing the homework for this chapter, because this is kind of like your little cheat sheet. Okay? And it will help you. Okay? I would like to make a very quick note here. Normally the number here is the what? The atomic mass, or sorry, the atomic number, right? Okay? Or how many protons, right? Here, these two, for the electron and the positron, okay? The subscript number on the left is not the atomic number or the number of protons, but the charge, right? Because the electron is negatively charged and the positron is positively charged. Okay? Everyone with me?
Yes.
Very good. So, we're going to talk a little bit about nuclear stability, and then we're going to go back and write out nuclear equations and get some practice. Okay? So really, when we're looking at nuclear stability, we have to remember that there are really two kinds of forces that involved in an atom. Okay? There's the electrostatic force, i.e. the attraction of plus or minus, or the repelling of plus and plus. Of course, there is the repelling of minus and minus, but we're not looking at minus charges, we're looking at protons. So really, it's either plus or minus or plus and plus. And there is the nuclear force, or in physics they call it the strong force, a force of attraction between nucleons that act only at short distances. Okay? So the nuclear force is much stronger than the repelling electrostatic force of two protons, and that is what holds the nucleus of an atom together. Okay? Think about it for a second. If you're sitting in the nucleus of an atom, you're inside, okay? There's a lot of what? Protons, right? And they're all positively charged. Do you agree? So if you have positive, 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 positive everywhere in that nucleus, aren't they repelling one another? They must be. The electrostatic force. They must be repelling one another like, I don't want to be next to you. You're positively charged. Please get away from me, right? Think about it. Just take a moment. When we were doing box diagrams a long time ago in 151, we said Hund's rule was that the electrons are mutually repulsive, right? So that's why you don't want to put two arrows in the same box right away. You put one arrow in one orbital, then the one electron in the next orbital, and then the next orbital. And then if you really don't have a choice, then you double up. Do you guys remember Hund's rule? Okay. Why? Because electrons are all negatively charged, they repel each other. So they're like, don't be next to me, go in the next box, go in the next orbital. Right? So why is it that in the nucleus of an atom, the protons aren't acting the same way, like, get away from me. I'm positively charged, you're positively charged. Get away. Why doesn't it just fall apart? Because of the neutrons. Very good. Because of the neutrons due to the nuclear force. You can think of nuclear force like this. If I have mass and you have mass, and we're very, very, very close together. And this only works if we're very, very, very close together. Okay? The closer we get together, the more strong force or nuclear force is holding us together like glue. Okay? This doesn't work with electrons because electrons are not that close together and electrons are negligible in mass. Okay? But protons and neutrons have mass. And they're very, very, very close together, right? We learned in 151 that the nucleus is very dense, right? Very packed, okay? So the neutrons are very close together. And because they're very close together and they have mass, there's an attractive force, okay? And this, we've seen it, this kind of strong force before. It wasn't called nuclear force. Think back to elementary school, okay? What is it that holds the planets around the sun going in a circle? Gravity, or because the sun has a huge mass, the earth has a mass, right? So there's an attraction there that holds the planet in orbit around that star, in this case our sun, right? That's why earth is not hurtling out towards the heliosphere, right? Right, okay? Because the sun has huge mass, earth has mass. There's an attraction there called the strong force, okay? And the closer and closer and closer you get, the greater the strong force. So because in an atom, the protons and especially the neutrons are very, very close together, the strong force is astronomical. And that is what holds the atom together. There is an electrostatic force repelling, but the strong force is much stronger than the electrostatic force. Does everyone understand the story that I've told here? Okay? So really, let's read that sentence again. The nuclear force is much stronger than the repelling electrostatic force of two protons, and that is what holds the nucleus together. Okay? So if you think about it for a second, you say, the more neutrons you have, the more strong force you have, right? Because if I am an atom, sorry, I'm a neutron and you are a neutron, we're very, very close together in the atom, strong force. What if Shimona joins us? Now there's strong force between you and me. What if Krishna joins us? Now we're like four all together and we're all strong force, right? So the more neutrons you have, the more strong force you have, the more holding power you have, right? So really, you can think of the neutrons as nuclear glue, right? That allows the protons to stay together. And the more neutrons you add, the more nuclear glue you have. And the more stable your isotope becomes. Okay? And remember, neutrons are uncharged, so when you add more and more neutrons, you aren't adding more and more electrostatic repelling force to counteract your strong force. Okay? And each neutron is attracted to neutrons and to protons by the nuclear force. So therefore, adding neutrons to a nucleus increases the attractive force, or the strong force, or the nuclear force, holding the particles of the nucleus together without increasing the amount of repulsion from the positive and positive charges. Okay? Do you understand that? Okay? Because this kind of question will appear as either an explain, why doesn't the nucleus just fall apart because it's full of positive charge, or it'll be a multiple choice question, right? Right? And as you know, I like questions about explain and write out complete sentences, right? Okay. So, how does this have anything to do with nuclear stability? Well, let's think about it. The more nuclear glue you have, the more stable you should be, right? Yes? Think about it. Remember when you had those little popsicle sticks and in kindergarten and you built these little popsicle houses? You stacked them on top of each other like logs. Did you do this in elementary school? Kindergarten, right? Okay. If you were the child who was stingy with the glue, right? You're carrying your little house back home and you fall apart, right? Or you're like me and you're just like glue everywhere, right? Right? And it's really strong, right? So it's a good gust of wind will not affect it, right? Same thing with atoms. The more nuclear glue you have, the more stable you are, right? Make sense? Okay? So, similarly to electrons having shells of 2, 8, and 16, because 1s, then 2s, 2p, then what? 2s, 3s, 3p, so on and so forth, right? Okay? Those things are stable because the shell is full, right? Now, in a nucleus, we don't have shells in that sense, but we have shell models of the nucleus in which it's in the nuclear model in which the neutrons and protons exist in levels or shells. This theory states that the magic number, okay, is the number of nuclear particles in a completed shell of protons or neutrons. For protons, these magic numbers are 28, 20, 28, 50, and 83. Okay? If you're looking at number of neutrons and the number of protons and how many there are in ratio to one another, we understand ratio? Okay. There is a band of stability that is a region in which the number of neutrons and protons results in a stable, non-decaying atom. Okay? The band of stability is this like dotted like pathway all the way up to the top. Do you guys see there? Okay. Notice in the very beginning, so this red line indicates not the band of stability, but n equals z. What does n equals z mean? What is n? Neutrons. What is z? Number of protons or the atomic number, right? Same thing, right? Okay. So this red line means that what? N equals z means that the neutrons equals the protons. Okay. So at the very beginning, if you look at your periodic table, okay, n does equal z. Okay. Let's think about it. Let's look at carbon. Carbon is 6 protons. Its mass is 12, so its proton and neutron number is 6 and 6. Okay, let's look at nitrogen. One box over. 7 and 7 give you 14, which is the mass, right? Let's slide one more over. Oxygen. 18. So what? What? 8 and 8 is 16. Sorry, 16. Need more coffee to do math. Right? 16, right? So on and so forth. Right? Look at calcium. Let's go all the way to calcium. Calcium is box number 20. It is 20 and 20, which gives you 40 as the mass, right? So in the very beginning of the periodic table, most elements are fairly n equals z, or protons equals neutrons in terms of number. Okay? And they're very stable. These are very stable. Okay? But notice, as you get further and further out, okay, now here, you have no elements where n equals z. Let's look at 60. Let's look at box number 60. Let's find box number 60. Have we found box number 60? What is box number 60? Neodymium. Neodymium. Okay. Have you guys heard of neodymium?
Nope.
It's a rare earth metal. It's used to make very strong magnets. They've been mining it out of the earth in China for the last 20 years, and now You can buy like buckyballs, the little tiny magnet balls. They're made of neodymium. No? Nothing? Okay. All right. I just thought you guys played with toys like I do. You should look them up, buckyballs. They're very cute. They're tiny little magnets, super strong. And they're like little tiny balls. And it was all over the news that kids were like consuming them. And they're really strong. So if, as the magnet is going through your intestines, and you have two magnets, like the kid eats two, it gets super attracted to one another because they're really strong magnets, right? And they tear a hole in the kid's intestines from the magnets being attracted to each other. So if you ever get the buckyballs from Amazon or eBay, don't consume them unless you want a perforated intestines. Okay? Okay. And they're made of neodymium. Okay? So, sorry, that was like a tangent. We're on box number 60. Okay? Is neodymium's mass 120?
No.
It is not. What is it? 144, which means it has more neutrons, okay? Why is it that as we get further and further and further out, so like 80, right, we have to have more and more and more neutrons for it to be stable? Why? As you're getting more and more higher in atomic number, you're gaining more and more protons. Do you agree?
Yeah.
Carbon was only 6, that's okay. Nitrogen was only 7, no problem. You get to neodymium and you have 60. And there are 60 protons all repelling one another. Right? 60 of us repelling one another. You need stronger and stronger nuclear glue, more and more nuclear glue to hold together your 60 protons, right? So you have to increase your nuclear glue, i.e. the number of neutrons. Okay? So as you get higher and higher in atomic number, you have more and more protons repelling one another. I repeat again, as you get higher and higher in atomic number, you have more and more protons repelling one another. That requires more and more neutrons to act as nuclear glue to hold together your nucleus. So as you travel up the band of stability, you will get further and further away from the ratio of n equals z. Because you need more and more neutrons or more and more nuclear glue. That makes sense. How are we doing? Okay. Now, it does help you to predict what kind of emission will occur when you have certain kinds of elements. Okay? So if you have a lot more neutrons and a lot less protons, it will undergo a beta emission. Okay? All the way up at the very, very top, if you have about 160 to about 80, it'll undergo alpha emission. And if you're here in this range where you have more protons than neutrons, you will often undergo either electron capture or positron emission. Either you will capture an electron or you will emit a positron. Okay? And we'll talk about why in just a second. Okay? But this table is going to help you when you're doing your homework and they ask you to predict what kind of process or what kind of emission will occur or what kind of decay will occur. How do you predict? You have to look at where you are in terms of the neutron and proton count. Okay? So, I would like you to look at your periodic table. If you're looking at it, you should take notice that after element 83, or around 83, okay, all molecular weights are in brackets or parentheses. Many of them have no decimal values. Is that true? Okay, at least the one that I pulled off here, you notice there are no decimal values. Okay? Who remembers from 151 why we have decimal values in the first place? Because of what? Isotopes. That's correct. Can you tell me a little bit more? Explain a little bit more. What about the isotopes? Each element, there are many different kinds of isotopes, right?
They get the abundance.
And right, there are different natural abundances, right? Let's go back to the very first slide we were looking at. Okay? All the way at the beginning, or the third slide, sorry. Okay? Look at it. Hydrogen has 3 isotopes. Regular hydrogen, the deuterium, and the tritium, right? And if you're looking at the natural abundance, like Andrew was saying, it is mostly this, and a little bit of this, and basically negligible amounts of this. Okay? So if I averaged the mass of all the naturally occurring hydrogen, okay, it should be mostly 1, with a little bit of 2. Do you agree? Okay? So if I averaged it, it'll be 1.008. Right? Because it's going to be a little bit over 1 because there's a little bit of the mass of 2 included in there. Right? Okay? So really, if you want something that has an average mass reported on your periodic table with lots of decimal points, what you need to be able to do is to go out into nature, collect some carbon, and then determine the natural abundance, right? How many normal carbons are there, i.e. carbon 12? How many carbon 13s? How many carbon 14s, right? Then you average them out. And we did that calculation in 151, okay? But now notice, back to what I was saying. After element number 83, all of a sudden, we have no decimal points, just bracket number, whole number, right? Integer, right? These elements are radioactive, meaning they decay very quickly. So their mass will change very quickly over time. Okay? And so it is impossible to attain an average atomic mass. Does that make sense? If you want to get an average mass of me, you just take me and you weigh me, every day. Right? Weigh me, day 1, let's pretend 100 pounds, pretend. Day 2, 101 pounds. Day 3, 105 pounds, little donut mishap, right? Yeah, then day 4 at Thanksgiving, 110 pounds, right? Then day 6, we went through a juice cleanse because of Thanksgiving, so we're back down to 99, right? Okay? You get an average and then you add them all together, right? But what if after Thanksgiving I disappeared? Can you still get an average? No. But that's what's happening, because when you undergo decay, you lose the number of protons, right? Then you are no longer that element. You've disappeared from, not disappeared, but basically that element is no longer there, right? You've become, like instead of Dr. Chang, I've become Andrew, right? Or I've become Shimona. Then well, how do I average Dr. Chang? Dr. Chang is no longer here. She's morphed into Andrew, right? Do you understand what I'm saying? So it's impossible to get an average mass, so they just give you an estimated mass. And that's why it's in brackets with no decimal points. Okay? You understand? Okay? So that's how you can tell which of those elements on your periodic table are radioactive, meaning they decay very quickly. Okay? I like this chapter a lot because it's a lot of storytelling. Storytelling 101 with Dr. Chang. You know there's a storytelling class here at Gateway? I could teach that class. I don't know. I've never taken it. But I think I could teach it. All right. There are different types of radioactive decay. Okay? And we're looking at the decay. And then I want you to look at what is emitted or what is gained. Okay? And remember our little cheat sheet up there. It might help you. Okay? Your alpha emission means that you emit an alpha particle, which is basically helium. Okay? A beta emission, what are you emitting out? What is this? Who remembers? An electron. Very, very good. Okay? What is the equivalent process? It is saying one neutron is breaking apart into a proton and an electron. Okay? A beta emission overall is one neutron. It is becoming one, oops. Proton plus one electron. Okay? It's different from a positron emission. And let's look. Okay? It is one proton, right? And it is becoming what? A neutron plus what? Be careful. Positron. Positron. Okay? You have an electron capture. Okay? And again, this is a slightly different. It is saying one proton plus one electron. That together combines together to become what? One neutron. This is just the opposite of this, right? An electron capture is the reverse of a beta emission. Do you agree? Do you have a question?
The neutron up there shouldn't be like 1 and 0?
Yes, sorry. Writing too fast. Thank you. Okay. But really, the electron capture is the flip side of your beta emission, right? Because here, a neutron splits apart into proton and electron. Here, the proton and electron combine to become a neutron. Okay? And last but not least, you have your gamma emission. Okay? And really, it is just the emitting of energy, pure energy. Should not change the mass. Okay? So we've got our 4 different processes. Well, actually 5, because there is an alpha emission as well that we covered at the very beginning, right? Okay. Anyone confused? No? Okay.
Should we put that on our periodic table?
If you think that will help you. If you think that during an exam you will get all stressed out and be like, crap, what was a positron? What was an electron? Well, if you don't remember what an electron is, I would be a little bit disappointed. Then you can write it down and refer back to it, okay? But you cannot, listen, you cannot write any equations down. You cannot write any of these kinds of things down. That would be cheating, okay? You understand? You can write a table down like this to help you to keep track of each kind of emission, but you cannot write example problems. We've covered this. No example problems, right? Just like you can write, for example, E cell is equal to E cathode minus E anode, but you can't write down an actual problem with all the calculations written out. That would be cheating, right? We understand. Tables and equations usually are okay. You cannot write down actual problems, and you cannot draw anything. Okay? No pictures. So don't draw that picture. Nobody should be drawing 226 balls anyways. Okay? We good?
Well, electron capture is not from -1 to 0.
It's not what?
It's -1 to 0.
Oh, I see. Should be 0. because an electron should have no mass, right? All right. Now, let's look at each one of these examples, okay? And we're going to look at an example of what it is, okay? So you have an alpha emission, okay? That's when the nucleus loses an alpha particle. Okay, an example would be this becoming this and this, okay? Now notice that the sum of the subscripts and the superscripts of products and reactants are equal. What do I mean by that? I mean that if you add 222 and 4, what do you get? 226. If you can imagine, this is like an equal sign, okay? If you add 2 and 86, you should get 88. That is a quick way to double check to make sure you're doing everything correctly, okay? And obviously box number 88 should have RA, and box number 86 should have RN, so on and so forth. These are quick checks, okay? Beta emission, okay? A beta emission, like I said, is when a neutron breaks apart into proton and electron, okay? So an example would be carbon-14. It breaks apart into nitrogen, and you lose 1 electron. Okay? Any questions? And again, if you notice, add up the subscripts and the superscripts. 14 plus 0 should equal 14. 7 and minus 1 is 6. Okay? The math should work out nicely. Now the mass is the same. Why is the mass the same? Because neutrons and protons have the same mass, and really what is happening in the beta emission is a neutron is becoming a proton. So the mass shouldn't change, right? Okay? You are losing a neutron, but you're gaining a proton. Again, mass should not change. But because you're gaining a proton, 6 becomes 7, the element identity has changed, right? You guys see that? You're gaining a proton. So it becomes 7. Box number 7 is nitrogen. We understand? Okay. Positron emission is when a proton breaks apart to become a neutron and a positron. Again, should the mass change in this kind of example? It shouldn't, because proton becomes neutron, has the same mass. Again, the element identity should change, because in this case you're losing a proton, right? The proton is becoming a neutron, so you're really losing a proton. So you're going to go down in proton count from 43 to 42. So you're going down from technetium to molybdenum, okay? And you're releasing out a positron. Is everyone following what's going on? How I'm determining what the element identity is? Yeah. Okay. When it comes to an electron capture, a proton becomes, is that right? Yeah. No, that one's wrong. This thing is wrong. I apologize. This thing is wrong. An electron capture should be a proton plus an electron becoming a neutron. Okay? It should be a proton plus an electron becoming a neutron. So imagine this is a plus, and that's an arrow. Okay? Again, should the mass change? No. Again, proton becomes neutron, same mass. Again, your element identity is what is changing, because you are going from proton and it's becoming a neutron. You're losing one, right? So you should go down from 19 to 18, from potassium to argon. Okay? So all of these, the mass shouldn't change. Really, it's just the identity of the element is changing, because you're either losing a proton or you're gaining a proton, right? In this particular case, you are gaining a proton. Here, you're losing a proton. Here, you're losing a proton. You see that? Proton becoming a neutron, so you're losing a proton. Think about it. Proton is becoming a neutron, so you're losing a proton, right? Proton becoming a neutron, so you're losing a proton. Neutron becoming a proton, so you're gaining a proton. Everyone with me in this fun game that we're doing today? All right. Gamma emission. Okay, all it is saying, and this is the easiest of all of them, okay, is an emission of an excited nucleus of a gamma photon, not proton, photon, okay, corresponding to radiation and with a wavelength of about 10 to the minus 12 meters. Okay, so basically you're thinking of it as an atom is excited, then it relaxes down and puts out some energy. Very similar to what we did back in the day in 151, where an electron was excited, jumped up in energy, up in orbital, and as it relaxed down into the ground state, it released light, which we saw with our eyes, right? And depending on the difference in energy gap, we saw different colors, right? Same thing. We're saying here, okay, it's a metastable nucleus. It's excited, okay? And as it relaxes back down, it gives out gamma radiation, which is just pure energy. You're not losing mass. You're not losing any protons, okay? So notice 99 is still 99. 43 is still 43. The only difference is your metastable is now becoming normal, and it is releasing out your gamma emission, okay? Another example, okay, not one of these, but it's called a spontaneous fission, okay? Now remember, fission is the breaking apart of a nucleus into lighter atoms and the release of energy, okay? Of course, you have to release energy because before, when we were lots of nucleuses together, strong force, right? If you pull apart and release and get rid of a neutron or 2 neutrons or 3 neutrons, you're releasing that strong force, okay? So you're looking at it and you're saying uranium becomes deuterium, okay, plus iodine plus 4 nucleus, not nucleus, 4 neutrons, right? Okay. This is a spontaneous breaking apart or fission of the nucleus because uranium is not stable. It is radioactive. It will decay, okay? And one of the pathways it decays is it becomes smaller parts, okay? Called spontaneous fission. With these kinds of things, you just always need to make sure your subscripts and superscripts add up together and they equal one another, left and right of the arrow, okay? So now that we've gone through all of these things and all of these types of reactions, okay, let's do some examples, okay? Now on the homework, you won't have the boxes there that I've drawn so nicely for you, but just to help guide you at the very, very beginning, I put in some boxes, okay? So really, you have Ra, it becomes and if you don't like the boxes, you don't have to draw them. It's up to you, okay? So it says to write the nuclear equation. So we're going to finish writing this out. For the radioactive decay of radium-226 by alpha decay to give radon-222. Okay? I already see a typo on here. Okay. So there's a typo here. We'll fix it in just a second. All right. So what is radium-226? It's in box number 88. Box number 88. Okay? So 226, box number 88. What should I write here? Where should I put 88? At the bottom. Where should I put 226? Okay, because that's the mass. Okay? And it is an alpha decay. So what am I losing? Helium, or an alpha particle. So I should be losing helium with a 4 and a 2, right? This is my alpha particle. And if you can't remember, let's go back. Alpha particle is helium 4 and 2. Okay? So this obviously cannot be right. Okay? What number must be here? What number must be here? I'm hearing it, 86. Okay? And box number 86 tells me the element symbol or the atomic symbol. Where's box number 86? Let's find it. What is it? Radon, so it should be Rn. Okay? See, I made a mistake typing these up too quickly. Okay? And last but not least, how do I know the mass of Rn? Subtract. 226 subtract 4 is 222. Can we do this? Yeah? Let us pull out our homework booklet. Yes, they're decaying. They're just called emission or capture, depending on what is going on. So if you're emitting out either an electron or a positron, then it's an emission because you're putting out. Because either, so do you remember that? Okay, so his question is, no, it's okay. His question is, why do certain things undergo certain emissions or decays or et cetera, right? You have to go back to that picture on the stability, that graph on stability. It's okay. You're looking at this picture here. Okay? You have your band of stability, that band of dots that represents something stable. Okay? So if you have here 22688, okay, how many neutrons? How many protons? How many neutrons? What is Z equal to? Z is equal to 88, right? What is N is equal to? 226 subtract 88 is what? Uh-oh. Can't do math today. 138. Okay. Let's find where we are on this picture, shall we? Okay. 88. So this is 90. Okay. So 88 is a little less than this line here. And 138 is, I'm not tall enough. It's all the way up there. Do you see where 140 is? Do you guys see? Yeah. Okay. That was like about a foot taller. Okay. So if we're there, it's going to undergo alpha emission. Does that make sense? If I am an atom here and I'm here, I'm going to undergo beta emission. Okay? Beta emission, let's look. Beta emission is what? A neutron becoming proton, right? Why? Because if you're out here, you have too many neutrons, so you want to fall back to stability, so you want to convert some of those neutrons into protons. So you can fall back into this band of stability. Right? In this particular case, if you're here, you have more protons than neutrons. You want to get more neutrons, more nuclear glue, right? So you're going to undergo either a positron emission or electron capture because in both of those cases, the proton is converted to a neutron, right? The second two examples there, right? Proton is converted to a neutron in both of those cases. So really, you're looking at the N versus Z ratio to be able to determine what kind of process it will undergo. Does that make sense? That's a good question. There are homework questions exactly what you asked. Okay? So now let's go back to the homework questions, the homework booklet. Okay? So we are on page 73. 73. Okay. Let's go to 20.35. You see the third problem down? 20.35. Okay. What does it say? Thorium is a naturally occurring radioactive element. Thorium-232. Okay, what happens to thorium-232? It decays by emitting what? Single alpha particle. So decays, I would say the important keyword there is alpha particle. Keep going, what does it say? Produces what? Produces. Okay? So, what we would like to do is write an equation similar to that. Okay? So how would we go about doing this? Start with thorium. Okay, so let's find thorium. Box number 90. So what is the symbol? And where should I put 90? Good.
And radium is 220.
But wait, hold on. We're still 28?
I have 220 on mine. Yeah, but I have 220.
228. Okay, okay. But back to thorium. What number goes here in the top left-hand corner? 232. Okay. It is decaying and forming two things. What are the two things?
Radium and helium.
So what is radium? Box number?
88.
It has a mass of?
28.
And it is producing also alpha particle. Okay. Now, if I was doing this on a test, how would I check to make sure that I did it correctly? How would I check? Add the bottom and the top numbers. So 88 plus 2, does it give me 90? Yes. 228 plus 4, does it give me 232? Yes. Okay, this is what I mean by checking as you're doing the exam. Okay? Are we feeling comfortable? Okay. Next question on the exercise. Potassium-40 is a naturally occurring radioactive isotope. Okay. It decays to calcium-40 by beta emission. Okay. So you're starting with potassium-40. Okay. And it is becoming calcium. Okay. 40, and it decays by beta emission. So when you are beta emission, what are you emitting? What are you emitting? An electron. Beta emission is the first one on the board there. You should be emitting an electron. Okay. Potassium is 40? Is that the mass or the atomic number?
Mass.
It is the mass, so it goes in the top. Calcium 40, also the mass. What number must go here and here? 20 for the calcium, 19 for the potassium, because they are in box number 20 and 19 respectively. Okay? Again, how do I quickly check? I'm going to add 40 and 0 and get 40. 20 minus 1 should get 19. I'm good to go. Okay? Example 20.2. Technetium-99 is a long-lived radioactive isotope. each nucleus decays by emitting a beta particle. Okay? What is the product nucleus? Okay? So again, we're starting with our box number technetium, which is box number 43. So where should I write 43? And it is 99, so 99 is the mass. Okay? It decays and emits a beta particle. What is a beta particle? Just an electron. Okay? So it should be emitting plus 0, minus 1 e. Right? Okay? So what is here? How do I figure it out? How do I figure it out? So what must be here depends on what number is here, right? So what number must be here? Make it true. 45. Do you guys understand what I'm saying? 45 and then minus 1 gives you 44. So what is box number 45? Rhodium. Oh, sorry, 43. Sorry. So then this would be 44, which would change the element to what? Oh, ruthenium. Okay, good. Last but not least,
99.
so this is what we call the product nucleus. Okay? And this is what we call the, what do we call this in the problem? Very good. Any questions? All right, next one. Plutonium, 239. Box number 94. Let's all find box number 94. Okay? Since it is in box number 94, that should be the number here, and it is 239. Okay? It decays by alpha emission, with each nucleus emitting one alpha particle. What is an alpha particle again? Very good. So again, how do I figure out what is the nucleus here? The nuclear product. Product nucleus. So 94 minus 2 is 92. Let's all look in box number 92. Okay. Uranium. And we're just going to do a quick little 239 minus 4, and we get
235.
what? 235. Again? You good? Okay. The hardest part is the mental math and subtracting numbers. I have a student in my 151 class this semester. It's like a beautiful mind. So we're doing, have you guys seen that movie? No? And so we're doing, right now we're doing Lewis dot structures, and you have to count valence electrons. And so I'm like 3 times 8 plus 6, and she just like magically comes up with a number before I can even like add in my head. It's like a beautiful mind. It's wonderful to have her in my class. I am getting a little lazy with the math, though, I got to tell you. And when she makes a mistake, nobody catches it. All right. So now, this is what we were talking about. You know, Andrew and I, and when Andrew asked the question about what kind of decay, what kind of emission, what kind of capture does it undergo? How can we tell? Right? And it really, really depends, if you're looking at it, on what kind of ratio you have between your N and your Z. Okay? For example, here you have beta emission, right? So you have 9943. So if you have 43, you're approximately here. Okay? 99 is here, right? Right underneath 100. You're right here. Right? So you predict it should undergo beta emission. Right? Because you have more neutrons than protons. So you would like to lose some neutrons to get back to your band of stability. And undergoing a beta emission transforms your neutron to a proton. So you're decreasing the number of neutrons, increasing the number of protons, getting back to that magic ratio of around N equals Z. Does that make sense? Okay? And you have various areas, okay, depending on where you are. Okay? For example, if you're in the electron capture and positron emitting area, the isotopes there in this area here have more protons, so they're more likely that a proton capture happens, or an electron capture where a proton breaks apart into a neutron and a neutron and a positron, we have positron emission. In either of those cases, either positron emission or electron capture, the proton is being converted into a neutron. Right? Okay? And if you are here, isotopes have more neutrons, more likely that that neutron will break apart and become a proton. Okay? Kind of is reiterating what we had already said. Okay? So a series of radioactive decays often will occur until you get to a stable nucleus. So if you have uranium-239, it'll undergo an alpha decay, then a beta emission, then alpha, 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 beta, beta, alpha, and so on until you get to something more stable like lead or tellurium. Okay? Wherein the mass is smaller and it is no longer radioactive. Okay? Any questions? Nuclear bombardment is the opposite of a nuclear fission. This is an idea where you have two elements and you bombard them together. Bombard means like collide them together. Okay? And it forms a heavier element as a result. Okay? It's like Dr. Chang colliding with a donut. Becomes a heavier Dr. Chang, right? Okay? Same thing. Your nitrogen, it comes into collision with your alpha particle. Okay? The result of that is oxygen, which is heavier. Okay? And of course, it comes out as a side product, one hydrogen atom. Okay? Now, just like in the last chapter when we said if you have two half reactions, you've got your oxidation and your redox, we have a shortcut notation, right? It's called the notation for voltaic cells. Okay? We have a shorthand or abbreviated notation, again, for this kind of situation, where you have nitrogen. Your incoming particle is your alpha particle. Your ejected particle is your P, because this is really a proton. Hydrogen is just a proton, right? And then out comes your oxygen as your nuclear product. Okay? Any questions? Okay? With these kinds of abbreviated notation, a neutron is N, a proton is P, A deuteron is D, and an alpha particle is just alpha, Greek symbol alpha. Okay? Now, the application of what we just saw here of nuclear bombardment is the particle accelerator. Okay? A particle accelerator is used to accelerate electrons, protons, and alpha particles and other ions to very, very high speeds. Okay? Because, listen, if you just take helium and you put it in a box or in a container with some nitrogen, they're just going to float around happy as can be. They're not going to react with one another. Do you understand? They're not traveling at high enough speed. They don't have enough energy. They're just going to be like, doo-doo-doo, I'm a gas in a container. I am helium. Nice to see you there, nitrogen. Okay? Nothing is going to happen. You can leave it there for 20 days, 50 days, 100 years. Nothing will happen. Right? Think about it. This is what's in our air, right? We have in our air, we have helium, we have nitrogen, we have oxygen. It's not like they're reacting together, right? They're just existing, okay? The only way to get this kind of a bombardment to happen is if the alpha particle or the ion is traveling at really, really, really high speeds. And then at the very end, it's accelerated so much, and then it hits the nitrogen, or it hits whatever atom you're trying to bombard. And then, boom, out pops the oxygen. You guys understand? So really, what you need is a particle accelerator to accelerate, to speed up, to give that alpha particle enough energy. Okay? So that's what really, you hear about people building these huge particle accelerators, right? Where people are like traveling around the particle accelerator on like little bikes because they're so big, right? What you're doing is you've got this long chamber, okay, and it's basically being accelerated every single time it passes through the two bands of high frequency voltage. Okay? So the positive ions are introduced to the center. A fraction of the ions will cross the gap between. Okay? And so basically every time it crosses the gap, it gets faster and faster and faster and faster and faster. Do we understand? Think about it. It's like, okay, you're a positive charge, right? And every single time you go past the positive charge, it's like repelling, gives it some speed. Repelling gives it some more speed. Repelling gives it some more speed. And every single time you're doing that, you're passing one of these voltage locations, it actually goes faster and faster and faster. Right? Because that little repelling force will give it more speed. Repelling it, more speed. Right? Okay? And so eventually, at the end, okay, it will come out and it will be accelerated very, very fast. Okay? And this is your targeting material. So if you had like nitrogen here from our previous problem, or in this particular case you have molybdenum and you're speeding up a deuteron, okay? And so they hit each other at this target material. Okay? And then they will have a detector at the very, very end that can detect what comes out. Oftentimes people have no idea what's going to come out. They just know, I'm going to bombard this with this and see what happens. Okay? So an example here would be the molybdenum. You're bombarding it with some deuteron. You get out technetium and a neutron. Okay? And the way to write this or represent this as a symbol is our targeting material was the molybdenum. We're hitting it or bombarding it with the deuteron. Remember, out comes the neutron and then the technetium. Right? Any questions? Okay. So let's take a break here. Take a break here, and then we'll come back and finish this chapter. Okay, let's take a break. Yes, that's how we were looking at it. boson, because they're trying to break apart, I think boson is even smaller than a proton and a neutron. So they're trying to break out apart the proton and the neutron, so they're looking at this boson. They're trying. All right. All right. Now that we have a little fun with simple math, adding protons and neutrons, math gets a little bit more involved, but really it's just conversion factors for the most part. So now we're going to look at the rate of radioactive decay. Okay, we're looking at all these heavy elements, elements beyond element 83, so they're heavier. Okay, and we're looking at the rate of decay. Okay? They're not usually affected by temperature or pressure of the chemical environment. It really is affected mostly by the identity of that heavy element or that element. Okay? So rate is equal to K. K is the radioactive decay constant multiplied by N sub T. The capital N, little t, subscript. That capital N of T is the number of radioactive nuclei at time t. How many radioactive nuclei are there at a specific time, which we're going to indicate as t? Okay? So let's look at an example. It says the decay rate of 1 gram of radium-226 is 3.7 times 10 to the 10 nuclei per second. That nuclei per second is the rate. Okay? They would like you to solve for K, or the decay constant. Okay? So let's write down what we know. We know the rate, 3.7, 10 to the 10th nuclei per second, given to us in the problem. Do we know N of T? Do we know the number of radioactive nuclei? Not explicitly, but we do have grams, right? This is something like we did before in 151. How do I convert from grams to number of atoms? What was the roadmap? Grams to moles, moles to atoms using Avogadro's number, right? Same pathway, same roadmap. Grams to moles using the atomic mass, which is 226. Okay, you don't even have to add anything up. You just 226 is given to you. Okay, then moles to nuclei using Avogadro's number. Just like we did moles to atoms. Atoms are nuclei. They are the same thing. Okay, and so we should get, after all of the math, 2.7 times 10 to the 21 nuclei. Okay, of the radioactive isotope. Okay? Then to solve, really, is just plug in your rate, plug in your N of T, solve for K. Right? I should make the exponents up high. Sorry. So it's 3.7 times 10 to the 10th then divided by 2.7 times 10 to the 21, which is your n of t. And you end up with 1.4 times 10 to the negative 11. Notice there, what are the units for k? Seconds to the negative 1. Nuclei cancel out. You have 1 over seconds, or seconds to the minus 1. Okay? Any questions? This is very straightforward math, actually. All right. The rate of decay often is expressed in units of Curies. Like, do we know a famous Curie?
Yes.
Right? Okay. Lady from Poland. She died of, well, radioactive isotope exposure. We'll talk about that at the very end. Okay? But because of all her hard work, even though she did die young, they named a unit after her. 1 Curie is equal to 3.7 times 10 to the 10 nuclei per second. Does that look like a conversion factor? Absolutely. Something unit equals something unit, right? Okay. So let's look. An example. 1.0 milligram sample of technetium-99 has an activity of 1.7 times 10 to the minus 5 Ci or Curies. Okay? Activity really refers to the rate. The activity is the rate. Okay? Decaying by beta emission, and they say, what is the decay constant? So they want you to solve for K. K. Okay? So let's see. How do you convert the rate into nuclei per second? The first thing you need to do is convert the rate, right? So let's write down what we know. We do know that the original rate given to us in the problem is 1.7 times 10 to the minus 5 Curies. I would like to convert this to nuclei per second. So what unit must be here? Curie. I'm converting it into nuclei per second. How do I find these two numbers? From my conversion factor up high, 1 Curie is equal to what? 3.7 times 10 to the what? 10th nuclei per second. This is very simple math. What is 1.7 times 3.7? Pull out your calculators. Follow along. 1.7 times 3.7. 6.29. So I'm going to go 6.3 times 10 to the 5th. Okay? My units are nuclei per second. So do I have the rate now in nuclei per second? That's good. I do need to solve for n of t, the number of nuclei. And I have 10 milligrams, that's my amount, of my technetium. Roadmap is to convert from milligrams to what? Good. And then from grams to, and then from moles to, boom. So, thank you. Important to copy the problem right. All right. Grams to milligrams. What is the conversion factor? Everyone should just be able to know this. 1 gram? 10 to the third milligrams. Very good. Grams to moles. Technetium 9 to 9. 1 mole, 9 to 9. Moles to nuclei. Conversion factor is Avogadro's number, 10 to the 23rd. 6.00, 10 to the 23rd. This comes out to
6.1 times 7 to the 2.
Someone should check or double check, okay, the math. So my milligrams cancel out, my grams, my moles all cancel out. I am left with nuclei as my unit. Okay. Now I solve. And remember, the rate is equal to K times the number of nuclei. So really, K is equal to what? Perfect. The rate divided by the number of nuclei. So really, K is equal to 6.3 times 10 to the 5th nuclei per second, all over my 6.1 times 10 to the 18th nuclei. And again, don't put all of this in your calculator. That's a waste of time. 6.3 divided by 6.1 is? Huh? 6.3 divided by 6.1 is? 1.03. So I'm going to put 1.0 times 10 to the 5 minus 18, or? And what are my units here? S to the negative 1, or 1 over seconds. Okay? Any questions on how to do this? Is this not just conversion factors all over again from 151? Yes, right? Really, there is not that much math. My 151 students should be able to do this. Let's put it on the exam and see what happens. All right. The half-life. And we've talked about half-life before, right? Okay. Is the time it takes for 1/2 of the nuclei to decay. Okay. We talked about half-life back in chapter 13 when we talked about kinetics, where we said if you had 1,000 molecules of A, the half-life would be when you have the time elapsed and you have how much? 500, or half. 500 molecules left, right? Same principle, exact same principle, okay? Half-life is determined by measuring how long it takes for half of the sample to decay, okay? Calculated from the radioactive decay constant K. And if we remember from before, T of 1/2 is equal to 0.693 divided by K. And remember, K is your decay constant. Okay? This calculation is necessary, especially if half-life is a long time. Okay? For example, uranium-238 has a half-life of 4.51 billion years. Billion years. So is it decaying very, very fast? No. Okay. And a graph of half-life, we've seen graphs similar to this before in the other chapter, chapter 13, on kinetics. It's like if you had, for example, 1 gram, half of that would be 0.5 grams. So the time it takes would be about 10 days. Then another half-life would be half of 5, or 2.5, so on and so forth. Right? We've seen graphs like this before. All right. So how will we use this equation in calculating half-life? Let's look. The decay constant for the beta decay of 99 technetium was obtained in example 20.7. We found that K equals 1 times 10 to the minus 13 seconds to the minus 1. Right? Okay. What is the half-life of this isotope in years? If you have K, you can calculate the half-life. Okay? So let's look. T of 1/2 is equal to 0.93 divided by the decay constant K, which we've calculated in the previous problem. That comes out to 6.9 times 10 to the 12th seconds. Because you have 1 over seconds, or seconds to the minus 1 on the bottom, or the, what is that called, the denominator? The denominator. When you move it up, it becomes normal seconds, right? Okay. If you converted that seconds to years, of course, we all know how to do this. Seconds to minutes, minutes to hours, hours to days, days to years. Again, an exercise in conversion factors. Okay? That comes out to 2.2 times 10 to the 5 years. Is that a long time? Yes. It's a long time. All right. The longer the half-life, the more stable it is, right? Think about that for a second. The longer the half-life, the longer it takes for it to decay, the more stable that element is. Okay. If you're trying to do an experiment and it is very stable, there's no rush. But if you make a radioactive element, say like by bombardment, and then it's not stable, you want to use it right away. Right? There are examples in your book, in chapter 20, that tell little stories about the usefulness of all of these isotopes and how people use them in medical situations, in PET scans. Okay? The problem with a lot of these radioactive isotopes is they're not that stable. Their half-life is short. So then you've got to make it right away and then use it right away. Otherwise, if you make 10 grams and the half-life is 3 days, you've only got 5 grams left if you take a long weekend. Right? If you take Thanksgiving, your 10 grams has become 5 grams. Right? If you take spring break, your 5 grams has become 2.5 grams, so on and so forth. You see what I'm saying? Okay. So let's look at another example. Again, this is really just conversion factors all over again. Okay. Tritium is hydrogen with 2 neutrons, so 3 and 1, is a radioactive nucleus of hydrogen. It is used in luminous watch dials. Okay? So have you seen those watch dials where it doesn't require any battery, the numbers just glow, luminous? Okay? That's because the numbers are embedded with tritium. Okay? Tritium decays by beta emission with a half-life of 12.3 years. Okay? So that is T1/2, right? 12.3 years. Okay. What is the decay constant K in seconds to the -1? That's the first question. Okay. And the second question is to figure out what is the activity, i.e. the rate in curies of a sample containing 2.5, what is this fancy UG? Micrograms of tritium. Very good. The atomic mass of tritium, they give it to you as 3.02 AMU. Okay? So they would like you to first solve for the decay constant K. Right? So let's do that. We know that K is equal to 0.693 divided by T to the 1/2. Okay? So we're going to rearrange this into K is equal to 0.693 divided by T1/2. We've just rearranged it. No one needs me to do that, right? Okay. So we're going to say T1/2 is equal to 12.3 years. Okay. So really we're converting from years to what? Years to seconds. So years to days, days to hours, hours to minutes, and very good. Okay, so 1 year, 365. Learned that in kindergarten. 1 day, 24 hours. Also learned that in kindergarten. 1 hour, 60 minutes. 1 minute, 60 seconds. So really, T to the 1/2 is equal to what? 3? I heard 3. 3.88 times 10 to the 9. Someone double check her. It's okay. Seconds.
No, it's 3.
to the 8th. Does everyone agree? Okay, that's consensus. Now we're solving for k. So k is equal to, and we're using this equation here, 0.693 divided by our t1/2. This comes out to and my units should be s to the minus 1 or seconds to the minus 1. So this is my decay constant. Okay? Next, they would like me to solve for the activity. They would like me to solve for the activity. So really, they would like me to solve for the what? What do they mean by activity? The rate. And they would like it not in nuclei per second, but they would like it in Curies, right? Okay, so I've done this. I've solved for the decay constant, right? Now I'm doing the second question, okay? I do know what k is, okay? So what is my equation for rate? Remember, rate equals k times the number of nuclei, or n of t, okay? So do I know n of t? Sort of, I do. N of t can be solved by taking the amount of sample. In this case, it is 2.5 micrograms. This is the amount of sample. And I'm converting it from micrograms to grams, grams to moles, moles to nuclei. Very good. Okay? So therefore, what is the grams to micrograms? Is micrograms a small unit? It is. So 1 in front of the larger unit, 10 in front of the smaller unit. How many steps? 6. Okay. How do I figure out grams to moles? It is what? Tritium. It has a, it's given to you as what? 3.02. Okay? And again, Avogadro's number here, 6022 times 10 to the 23rd. This comes out to, again, don't do all of the math crazily. Just go 2.5 divided by 3.02 times 6.022. What do we get? 4.98 times 10 to the 23 minus 6 should be 17. Right? And again, I should be in nuclei. Okay, last but not least, we're solving for the rate. Okay, so we've found the n of t, right? So they would like us to solve for the rate or the activity. So really we would like to do k. We're going to pull k from up above, 1.79 times 10 to the minus 9 seconds to the minus 1. And we're going to multiply it by the nuclei. This comes out to okay? Did you say 8.91? Okay? And again, it's easier to use these power of 10s if you just take this number multiplied by this number and then just add your exponents here, negative 9 plus 17, right? Okay? And my units should be s to the negative 1 nuclei or nuclei per second. Same thing, okay? Now we would like oftentimes to determine the fraction of remaining nuclei. Okay? Now before we go all like crazy about, well, this is a new thing that I'm learning, Dr. Chang. We know all about fractions, right? Let's review fractions from when we were in elementary school, shall we?
Yes.
Let's do that. You have a pie from Costco because it is Thanksgiving. You cut it into 4 pieces. Okay, don't judge. Costco pie, 4 pieces. For breakfast, you ate one of those pieces. So good. With a little bit of coffee or hot cocoa. So good. What is the fraction of pie that I have consumed? How did we get 1/4? 1 is what? How much I've eaten. 4 is, where did the 4 come from? Total amount of pieces. Do we understand fractions? Do we understand fractions?
Sure.
Okay. This is the small amount. This is the total. Okay? So now, same thing, but instead of eating a piece of pie, we're going to count how much nuclei is decayed. It's almost like eating, right? Right? So really, the fraction is equal to n of t divided by n of 0. What does n of 0 stand for? If I had 4 nuclei to begin with, what is n of 0? 4 nuclei. After a certain time, you only have 2 nuclei remaining because the other 2 decayed. So then what is n of t? 2, right? N of t is 2, right? We understand? Remember, n of t, the definition was the number of nuclei at time t. Right? N of 0, just like we had, I don't know if you guys remember, you should remember. Do you remember when we had a of 0? What does this mean? Versus a of t in our integrated rate laws? This is initial, the concentration at the beginning, right? This is the concentration at time t, right? So if you have n of t over n of 0, it's just the nuclei at time t, the nuclei initially at the very, very beginning. And the nuclei at the beginning should be a larger number because it hasn't decayed yet. Does that make sense? So now we're looking at this example. It says the fraction remaining, example 20.10, phosphorus 32 is a radioactive isotope, and it has a half-life of 14.3 days. Okay? So a biochemist has a vial containing a compound of phosphorus 32. The compound is used in an experiment 5.5 days after the compound was prepared. See, he went on a long break, 5.5 days. He went on like spring break, right? So it's very clear. The biochemist made the phosphorus 32, put it in a vial, put it on a shelf, and went for spring break. Right? Then he came back. Can he assume that he still has the same amount of phosphorus 32? No. Some decay has occurred. Okay? So it's saying what fraction of the radioactive isotope originally present actually is still there, actually remains. Right? So they would actually like you to find out nt over n of 0, right? So we're going to use this equation here. ln n of t over n of 0 is equal to minus kt. Okay? And just as a quick derivation, if t1/2 is equal to 0.693 over the k, okay, can I solve it in terms of everything expressed in t1/2? Do you understand what I'm saying? If k is equal to what? K is equal to what? 0 point divided by t1/2. Okay? If I plug this number into this number here, so this is k, right? I'm going to plug this expression into here. You guys see what I'm saying? Then really that becomes what? Negative 0.693 over t1/2 times t. Everyone with me?
Yes.
Really? I'm going to rewrite this equation so that it matches what's on the projector. ln n of t over n of 0 is equal to minus 0.693 times t all over t1/2. Do we understand how we got from this equation to this equation?
Yes.
Good. Very good. Okay. So let's use this equation. Okay. Your t, your original t is 5.5 days. Okay. You need to convert that to seconds, obviously. Okay. Your t1/2 is 14.3 days because your half-life is 14.3 days. Okay. And again, you should convert these two to seconds.
Do we have to convert to this?
In this particular case, you don't need to. Why?
Because it has 100 days.
Because it's a ratio, right? If I take this number and go days to hours, hours to minutes, minutes to seconds, then I do the same thing on the bottom, days to hours, hours to minutes, minutes to seconds. They all cancel out, right? Because it's like 1, right? So in this particular case, you don't need to convert to seconds. Okay? In other cases, like in the previous problem where you don't have a ratio of time, then you do need to convert to seconds. Okay? We're going to plug in our t and our t1/2. And therefore, our ln of n of t over n of 0 is equal to this. To get rid of the ln, we e both sides. E of this number gives you 0.77, or 77% is left over. Okay? That makes sense.
Yes.
Be very careful when you do the homework problem. Okay? N of t over n of 0 is how much remains. Okay? What if I wanted to know how much is used up? Or how much has decayed? Is that the same thing?
No.
It is not. What is how much has decayed?
Well, the amount you started with minus the amount that remains.
Okay, so how would I calculate that? If this is how much remains, how much has decayed is just 100 minus that, or 1 minus that, right? Do you guys understand?
Yeah.
If you had 100%, or 100 pieces, right? And 77 of that is lost, sorry, it is remaining, then you should have 33 pieces left, right? Oops. I repeat, I'm going to say that again. I didn't say that correctly. If you had 100 pieces and 77 remains, then 33 pieces were decayed or lost. Right? Or we can say 0.33 or 33%. Is that clear?
Yes.
Did I do that math correctly? Is it 23? 23. And this is not why I'm not a math teacher. All right. Now we're looking at carbon dating. Okay, now this is an example of how you would use an isotope, okay, a radioactive isotope, in an application. Okay? Really, the only reason we're interested in any of these situations is because they're very useful to us. Okay? So carbon dating is one of those things where you take an isotope, okay, and you can use that to help you to figure out how old something is, how ancient something is. Okay? So let's look at what happens. Okay? This is kind of like a story. So you got to follow along. Okay? So in the very beginning, you have some cosmic rays. And yes, that is a real thing. Okay? There are cosmic rays that are radiation from the space. Okay? And they are made up of protons, alpha particles, and some heavier ions. Okay? So because the cosmic rays from the sun enter the Earth's atmosphere, okay, these high-speed protons, alpha particles, and heavier ions will collide with an atom in our atmosphere. Okay, so what is in our atmosphere? What is in our air? For the most part.
Nitrogen.
Nitrogen is a major component of what is in the air. Okay, so it will collide or bombard a nitrogen-14. Okay, that nitrogen undergoes neutron capture, releases a proton, and gives us carbon-14. Is everyone with me? Okay, so how is carbon-14 different from carbon normal? Like a normal carbon, or a naturally occurring carbon? It's heavier by what? 2 neutrons, because carbon is normally 12 from your periodic table, right? Okay, so now the carbon is in the air. Okay, oftentimes it is carbon dioxide. Okay, and what happens to the carbon dioxide when it meets a tree or a plant or a flower? We call it carbon fixation. What does that mean? It takes carbon dioxide and converts it into sugar or glucose, okay, which then the plant links together and it becomes starch or cellulose, right? Depending on the alpha versus beta linkage of the sugar molecules. Do you remember this from biology? Okay. So what we have done is we have taken the carbon-14, that's carbon dioxide in the air, and it's become part of the plant as either its cellulose or its starch. Have we fixed this carbon? That's why it's called carbon fixation. It's now fixed in the plant. Okay? Then, as the plant is growing, okay, either you and I will come and eat the plant if we're vegetarian, okay, or a horse or a cow or pig, something like that, will come along and eat the corn or eat the tree or eat the grass, right? If you're a cow, you eat grass or hay, right? And that plant contains what? The carbon-14 from the air, right? From the carbon dioxide, which came from the cosmic rays, right? Okay? So, if you're alive, if you're a plant or an animal, you will always be either consuming a plant that contains carbon-14, or you will be, if you're a plant, you will be fixating carbon-14, right? Right? So one or the other. As long as you're alive, okay, you'll be going on a steak or on a piece of kale, right? Do you understand? So you will be constantly intaking carbon-14. So the amount of carbon-14 in your body remains fairly constant if you're alive. If you're alive. That's the key word there. The moment you die, or horsey dies, or cow dies, right? It's now in the ground, right? And it gets covered by volcanic ash. Or it gets buried in a box, if it's your pet rabbit, right? Okay? Is it at that point still consuming carbon-14?
You know,
No, it is not. So now, carbon-14 is a heavy isotope and it starts to decay. It's always decaying, right? So, and you are not replenishing that supply by eating. You are not replenishing the supply because you're no longer eating because you're dead, right? The plant is no longer fixating, if you're a tree, you are no longer fixating carbon dioxide because you're dead, right? So then, over time, the amount of carbon-14 starts to decrease. Decrease. The older you are, the less carbon-14 you have, right? Because carbon-14 decays to carbon-12. Okay? So what do scientists do? Scientists go out into the wild, they dig up a fossil, right? They take the fossil back to the lab, right? And what do? They scrape off a little bit of the bone, right? Or the plant sample, and they measure the amount of carbon-14 left in the sample. The less carbon-14 there is, the older the sample. Right? That's how people can figure out like pottery and fossils, how old something is. Because if it's 1 million years old versus 2 million years old, it should have less and less carbon-14. Okay? Do we understand this story? Yeah? Okay. So, let's look at an example of how we would work out the math on this. Okay? So you have a piece of charcoal from a tree killed by volcanic eruption. Okay? So you have a tree, it was happy and alive, fixating carbon-14, happy and alive, and then along comes a volcano, and the volcano erupts, buries the tree. Tree no longer alive. Now the tree is sad and dead. Okay? We understand this? Okay? This happened in Crater Lake in Oregon. Okay? So that piece of charcoal, so the tree was buried and then over time it became charcoal. Okay? So that charcoal gave 7.0 disintegrations of carbon-14 nuclei per minute per gram of total carbon. Okay? Present day carbon in living matter. That means that it's alive. Like you and I, like tree, alive. Okay? Gives 15.3 disintegrations per minute per gram of total carbon. Okay? So you've got your 15.3, that is your initial. The dead tree is 7.0, that's N of T. Okay? And T is what? T is what we're trying to determine, right? Determine the date of volcanic eruption. They want to know what is T. Okay? And they give you as a given half-life of carbon-14 is 5,730 years. How do we solve this? We rearrange the equation. T is equal to T1 half divided by 0.693 ln of n of 0 over n of t. We have T1 half, we have n of 0, we have n of t. Plug everything in. T comes out to, and again, you don't need to convert this to seconds because you just keep everything in years. Okay? If you don't report this in seconds, just keep it as years. Okay? So this T comes out to 6.5 times 10 to the third years, or 6,500 years ago, or approximately 4483 BC. Okay? Any questions? There will be a couple of questions like this in the homework where you have to use this equation. Now, there are certain amounts of radiation that won't kill us, but there are certain amounts that will eventually kill us. Okay? So we're looking at exposure in terms of REM, and REM is a unit of radiation dosage, and its subsequent health effect. So if you have 5 to 10 REM, it changes your blood chemistry. You have 50 REM, you start to feel nauseous. You have 70 REM, now you're vomiting. 75, you're losing your hair. 100, you're starting to hemorrhage inwardly. 400, possible death within 2 months. Okay? This kind of thing happens sometimes when you're working with nuclear material, radioactive material, right? The material doesn't, you can't see the radioactive effect, right? You can't see a positron or an electron or an alpha. You can't see it. You guys understand? So a lot of times people will work with it, they think they're protected, then they accidentally get exposed. And really there's nothing you can do really to cure them. If you get exposed, they can treat you for the pain, they can make you comfortable, but really a high exposure of like 2000 REM, you're guaranteed to die within a couple days. Yeah.
So how does the radiation therapy cancer patients?
So those kinds of radiations are not like this kind of situation where it's like 2000 at a time. It's much less, okay? And the effect of that is irreversible. Your body, so when you do radiation, when you have cancer therapy, right, they're trying to kill the cancer cell, right? As a side effect, hair loss, nausea, vomiting. I mean, they treat the symptoms. They'll give you like popsicles and things like that when you're undergoing this kind of stuff, right? Make you feel less nauseous, right? But really, the only way to recover is your body slowly recovers and grows back normal cells, and then you feel better, right? If you have blood loss, changes in blood chemistry, your blood will eventually go back to homeostasis. Your body has ways to adjust for that, but it's not like they're treating you for the exposure, they're just treating you as the symptoms, right? And they're very careful, they don't give you 2000 at a time. It's small amounts at a time, you keep going back, right? Eventually, the hope is you can kill the cancer cell before you are exposed enough that you die, right? It's like a balance, right? If they expose you too much, eventually you will die. They want to expose you just enough so that they kill the cancer cells, right? And they usually combine radiation therapy with chemotherapy, right? And chemotherapy is another kind of poison to your body where they're poisoning the cancer cells and hoping the cancer cells will die and your body will reproduce normal cells. And true, it's true. As you're taking in poison, your chemotherapy, you're also killing off normal cells. You are, right? So that's why you feel sick, you feel nauseous, because you're really taking in poison, right? And that the goal is hopefully you can get rid of the cancer cells before all of your normal cells are affected. Does that make sense? So on that happy note, congratulations. You have finished everything in 152. We have covered all that material. That was a happy ending, right? Cell death and cancer. All right, so as a very last thing that we're going to do today, we have about a little less than 10 minutes. I have the quiz from electrochemistry part 2. So let's put everything away. Let's put everything away.